All right, today we're diving into something that sounds like it's pulled straight from a sci-fi movie. Plastic that can actually conduct electricity. This is the incredible story of a Nobel Prize-winning discovery that completely flipped our understanding of what materials are capable of. Seriously, just stop and think about that for a second. We use plastic in our daily lives for pretty much the exact opposite reason. I mean, that's the whole point of plastic, right? It insulates our wires, it protects us from shocks. So the very idea of a conductive plastic, it feels like it breaks one of the most basic rules of physics. So what was this rule breaker? Well, meet the star of our show, trans polyacetylene. Yeah, it's a mouthful, I know. But this stuff, this simple-looking organic polymer, was the very first of its kind. It did something that, at the time, scientists thought was totally impossible. And in doing so, it kicked off a whole new field of science. Okay, so here's our game plan for today. First, we'll talk about the discovery of the electric plastic itself. Then we'll look at its surprisingly simple carbon chain structure. After that, we'll uncover the secret of the traveling defect. We'll see how scientists flip the switch with something called doping. And finally, we'll explore the huge polymer revolution this all started. All right, let's kick things off with the electric plastic. And look, to really get why this was such a huge deal, you have to understand just how, well, bonkers this idea was at the time. This wasn't just some small incremental step forward. It was a massive leap that went against everything chemists and physicists thought they knew. For ages, I mean, for decades, the rule was practically set in stone. It was as basic as what goes up must come down. You had your conductors, things like copper and silver, and you had your insulators, things like rubber and plastic. They were two totally separate categories. Period. End of story. Or so everyone thought. So how in the world did this one material just shatter that rule? Well, to get to the bottom of it, we've got to look under the hood, you know? As is so often the case in chemistry, the secret is all in its structure. And what's crazy is how simple it really is. Just picture a really, really long line of carbon atoms. Now imagine they're linked together in a specific pattern. One atom is connected to the next with a single bond. The very next one, it's connected with a double bond. And that's the whole pattern. Single, double, all the way down the line. That's pretty much trans polyacetylene in a nutshell. Okay, but wait. If it's just this simple little chain, how on earth does it carry electricity? This is where things get really, really cool. It's all thanks to this little quirk, this little defect that can actually travel along the chain. Now, this defect has a fancy science name, a soliton. But don't worry about the jargon. Just think of it as a kink in that perfect alternating pattern. It's a spot where the single-double sequence gets messed up. And here's the kicker. That kink isn't stuck in one place. It can actually move. So check out how this works. You start with your perfect repeating chain. Then a defect, our soliton, gets introduced. And this is the magic part. That defect isn't stationary. It starts to move, kind of rippling down the chain like a wave. And get this. This is the punchline. The movement of that defect, that is the electricity. It's literally a charge flowing through a piece of plastic. Mind-blowing, right? Okay, but here's the catch. There's almost always a catch, right? This plastic isn't just naturally conductive. You can't just pick it up and use it as a wire. It needs a little kickstart. Scientists had to figure out how to flip the on switch. And when I say flip the switch, I mean it. The change is absolutely staggering. In its pure form, polyacetylene is just a regular old plastic insulator. But then, after they do this thing called doping to it, bam! Its conductivity shoots up by thousands, sometimes millions of times. It's an insane transformation. So what is this doping process? Well, think of it like this. You're just giving the chain a tiny chemical push. You either add an electron or you take one away. And that one little action is what creates that initial soliton, that kink we were just talking about. Doping is what primes the pump. It creates the charge carrier that can then zip down the chain, turning a boring old insulator into a conductor. And all of this incredible science, it wasn't just for a textbook. It led to a full-blown polymer revolution. This wasn't some quirky lab experiment. It completely changed the game for technology, leading to stuff we literally can't live without today. I mean, look at this legacy. It's incredible. Every single time you look at that beautiful, super vibrant OLED screen on your phone, you can thank this discovery.
It's the reason we have things like flexible electronics. Yeah, think foldable phones. It's in lightweight batteries, those anti-static bags that keep our computer parts safe. You can even print electronic circuits now because of this. It's everywhere.
Which kind of brings us to this final thought. The whole story of conductive plastic is just this amazing reminder that sometimes the rules we think are unbreakable in science are really just suggestions, waiting for someone to come along and challenge them. It really makes you wonder, right? If we can make plastic conduct electricity, what other impossible rules are just waiting to be broken?